as well. So let's pay attention. Most of these are reviews so that we can remind and our understanding of wave propagation, and especially a simplified one, plane waves and spherical waves. And we are getting into a little more analytical and reviewing what we have done previously. So a general plane wave propagation, we can describe it as a k vector, which is a wave vector, and the k vector has a, you can decompose into like either x or z direction. So general like oblique angle propagation of a theta angle with respect to z-axis, you can describe the plane wave as a constant amplitude times e to the I k r minus omega t, but minus omega t term is always there, so we kind of remove that. We don't consider it for now. So k dot product and r vector, you can actually see as a k x sine theta. In this case, the k vector's x projection is a k times sine theta. So that's k sub x, x directional projection of the k and times the x. Likewise, kz equals sine theta, which is a projection component onto the z-axis. So while we remember that this is a plane wave, but what about from the point light source, and that will be like propagating throughout the space, which we're considered as a spherical wave. So that's from Helmholtz equation. The solution is a little similar but different in terms of A divided by R, and also by the distance of the z. So you can actually see those can be similar to a plane wave with respect to z is e to the I k z times e to the, remember, so here comes a Taylor series expansion, and now quadratic phase term is coming because these are like quadratic. So e to the I k x plus y square over 2z. So this is something we've seen. And but our interest is really put a screen over there to find out the intensity distribution in the end. So in fact, these are doesn't depend on x and y. So these initial components are kind of a constant. So we do not consider this one that much, and only this one becomes a kernel as we developed our theory of Fresnel diffraction or Fresnel integral. These are very, very important. Okay, so let's go back to check again a simplified version of interest, a specific plane of observation at z equals d. So now we can see like this one becomes the plane wave a times e to the I k, because we are interested in this on the screen, I k x sine theta. And while when the distance of d, so you can see the same as before, this is Fresnel, but also you realize that in what if at the point of interest is actually converging light. So Laxman, so can you guess what we have done from this second to the last one? Instead of diverging, when we go to converging, so what did we do from here to here? What are the differences in the change?
Yeah, negative I minus over here.
Exactly. Yeah. Where did we actually put the minus sign from this formula? Can you guess?
Over here, E minus I KT, E minus I minus I.
Yeah, okay. So in fact, my question was intended that the minus actually gets into the D. So instead of D, we put minus D. It's not onto the K because the directionality are the same from left to right. So here, what we are focusing on the shape of this, okay? So that's very important shape to remember what's going on over here. All right, so now let's get started with our understanding of plane waves, especially considering interference from two plane waves. The reason why we are considering from this is the viewpoint. Now we are kind of completely changing the viewpoint as a general or general kind of wavefront propagation, we could decompose that into a multiple of different angular plane wave summation with different amplitude and phase. And that can create any kind of pattern formation. So as a basics, we start with two plane waves. So when the two plane waves are having oblique angle of theta, what is the image when you place a CCD camera or film at z equals 0 plane? So that's the question we want to solve. And some of you already might have familiar with this. So this is going to make a interference pattern, and which is a sinusoidal. And what matters is we are dealing with a field, but in fact, our detectors are only deal with intensity, which is temporal average one. So for example, a CMOS camera or CCD camera measures intensity to detect, and that's field magnitude square. So that's, you want to keep that in mind. So let's do some understanding step by step. So let's consider two fields from F1 field and F2 field. So F1 field is the simplest form of plane wave onto the z positive z axis. So that's F1 is a times e to the I k z. Okay, do you agree? And then oblique angle, as we just say, F2 is a. Instead of this, now we have k x component of k sine times x plus k cosine times z. So that is the two field distribution when z equals 0. So you can see, just simplify when z equals 0. So that's this screen is over here. Then z equals 0, then you have only constant a. And z equals 0 is a simplified form of F1 and F2. So important thing is, in the end, you add up the total field because it's a field, electric field, you can add up. Okay, so like adding up these, and intensity is magnitude square. So that is, in general, we use complex quantities. So this means G times G complex conjugate. And you can do the math of this one, A squared, this one with complex conjugate, this one, and two, like not 2AB, but A times this complex conjugate, this times this one complex conjugate, that will result in 2A cosine kx sine theta. So that's what you can do the math. Okay, so in the end, how can you interpret what's going to happen? Here is, these are all constants. Okay, so it's more like 1 plus cosine kx sine theta, which will be intensity distribution onto this screen. Okay, hopefully this one is clear to you. So we draw this intensity distribution on the screen, which is z equals 0. Then what's going to happen is, so you remember that the previous slide, that a squared 2a cosine k sine theta times x, right? So with this, you can actually find out that 2 pi and the rest, and you can easily see when x, the period of this will be, instead of lambda, but lambda over sine theta. So the spatial period will be lambda over sine theta, and while the amplitude goes up and down by 2a squared. So that's what you can see over here. See? Okay. I think, oh, sorry. So these are all a squared. I just want to make sure there's some typo. So these are all a squared. So correct that. Okay. So now let's go back to the our little bit of basic understanding of Fourier transform, the principle of it. So the principle is arbitrary wave, like any kind of distribution of this wave in space, or in this case time, can be represented as a multiplicity of sinusoidal waves with different amplitude n phase or different weight of sinusoidal waves. So this one can be decomposed as, I would say, from spatial low frequency to the high spatial frequency. You combine this, and that can create any arbitrary waveform. So in the end, you can really think of arbitrary waves. So it can be expressed as superposition of sinusoids with complex amplitude. And this is a temporal, but I would say even in space domain, this applies completely the same way. All right, so then now go back to the plane wave versus a spatial frequency. So we are interested in the field at z equals 0, which is on the screen over here. And we realize that a times e to the I k sine theta times x. That's what we know. Now we want to compare with the reminding of Fourier transform formula. So you remember that the kernel is e to the I 2 pi u x. And the u is a spatial frequency of the x direction. So compare with this and this, you realize u is actually sine theta over lambda. So what does that mean? It's a spatial frequency. So when you think of theta equals, let's say 90 degrees. So if the wave just propagates along the x-axis, then u becomes, theta will be 90 degree and sine is 1, u equals 1 over lambda. So it's exactly spatial frequency. So you can think of that way. When theta is 0, then there's going to be no frequency, so u equals 0. So now let's graphically understand what this physical meaning of spatial frequency. So in fact, when theta is there, the wave propagates in this direction. And then, as I say, wavefront, we kind of dotted line. That distance between dotted line represents a lambda. And from this trigonometry, and you can find out the projection of this lambda onto this x-axis is, you realize that this is a lambda, and this becomes a cosine. Actually, one over the sine, because this is sine, this is lambda, this will lambda over sine. So that spatial frequency along the x-axis is now become a u, or 1 over u in this case. So spatial frequency u can be defined as sine theta of lambda. So this is how we observe things. And now we want to change slightly our viewpoint into a kind of angular spectrum concept. So spatial frequency as an angle of propagation. So we remember now that spatial frequency u, or this is in unit space, how many of the wave exists. That's the definition of spatial frequency. Okay, so this sine theta of lambda, and now you can see, because this u is along the x-axis, the spatial frequency. When theta is small, that's a kind of a lower angle, and that we can see as the sine theta is small, so it's a low spatial frequency along the x-axis. When theta is bigger and bigger, what you will realize is this u becomes higher, which means in space, this will be more packed along this x direction. Okay, so that means high spatial frequency. So in the end, really what we mean by spatial frequency is the angle of propagation of the plane waves. So when the angle is shallow, then you have low spatial frequency. When angle is high, high spatial frequency. And now it's time to remind you about the Abbe's definition of numerical aperture of the limit of resolution based on the diffraction. So you remember that? So when you have a sample onto the x, along the x-axis, if there's a high spatial frequency or fine feature, the first order diffraction will be higher angle. And that has a risk not being able to pass through your optical system. And that information could be lost in your image. That's why you get lower spatial resolution. While low spatial frequency or bigger features will have this lower spatial frequency that's likely to get passed through your optical system. So you can reconstruct lower, rather poor resolution, but you can easily reconstruct for that image. Okay, so far, really, there was a good question about why we are doing Fourier optics, and Sadav answered well enough. So really, the Fourier optics helps us to see the same phenomenon in a different angle, but it turns out that makes our life very, very easier and intuitive later on. So that's why we studied Fourier optics. And so arbitrary wave, you can consider that as a superposition of plane waves and with a complex amplitude. Either it has high angle, that means high spatial frequency, shallow angle, lower spatial frequency. So plane, we can consider this kind of generalized arbitrary wave as a plane waves with different angle of propagation or different spatial frequency. That's how we can understand the Fourier optics. So let's try to get a little familiarize ourselves with the spatial frequency now in 2D sinusoids. So let's consider on a screen, we have X and Y of these sinusoids that generally you can consider or describe this as a cosine to pi, let's say ux, u is a spatial frequency onto x, and vy. You can describe it this way. And you can easily consider this as a real space, but you can put I sine the same argument, and you can create this as a phasor, complex phasor form. So a times e to the I to pi ux plus vy. And here, what do I mean by u and v is spatial frequency. So really the period, spatial period is actually 1 over u and 1 over v. So you can actually consider it that way. Okay, so now we generalize this concept of an image. So now let's consider about the general arbitrary pattern of an image here in XY. This, what we really say is this very complicated general 2D shape can be in fact decomposed as many of sinusoids of 2-dimensional sinusoids superposition. So you can see this fine detail, which means spatial frequencies are different between different wavelengths or periods, and the angles are different. So all these one with different amplitude or weight, and phases are just summed, and that can result in this. So that's what really lies in the 2-dimensional Fourier transform. All right, so for example, so let's say this one as a general G of X and Y as a dysfunction, then you can consider, like, let's say in this one, U1 and V1, and this is complex amplitude of weighting, okay? So this is kind of a plane wave. You know that we can describe it as a e to the I, 2 pi U1X plus V1Y, and that's just 2D sinusoid. And these are kind of a basis function for 2-dimensional Fourier transform. And just likewise, U2, V2, U3, V3, U4, V4 of all these ones. So with this base and times multiplied by this weight, which contains complex amplitude and even phase differences. And that will form of this GXY. This is nothing but a graphical representation of our 2-dimensional Fourier analysis or transform. Okay, so that I write it this reminding you the formula of, hey, how are we gonna analyze our xy space of this generalized gxy, and that can be a summation of all these two-dimensional sinusoid as a base and its corresponding weight complex function of large G U comma V. And you just summed it between all different kind of U's and V's, and that will result this. So this is really the meaning of two-dimensional Fourier transform. And this has a profound impact on how we understand. So 2D Fourier integral is the summation of these complex weight, which contains magnitude and phase of the superposed sinusoid, and for the basis of 2D sinusoids. And the question now is, how can we calculate this G? And mathematically, this is now an easy question that now you are looking at. By knowing G, small g, you can find out this Fourier transform by use of inverse Fourier transform. And that makes it very easy in terms of formula. It looks almost same, just swapping this, and you put the minus sign here. So that's what it is. And this Fourier transform of G U comma V can be calculated by exactly the same way, but you are now summing onto space, and there's a minus sign here. Okay, so for example, let's make it a little easier for us. Just remove the y and only consider x direction. Then you have the gx function times this is e to the minus 2 pi ux, right? You are multiplying that, and then you are summing with respect to x minus infinity to infinity. Then it's a function of this u or g of u. So that makes it clear to you, right? All right. So we are talking, this is more of a mathematical right now, but this one exactly have the information in our optics too. So if we are living in space domain, any images can be described in G, X, Y. And now we have a just one-to-one correspondence of spatial frequency domain to describe this by a relationship of this two-dimensional Fourier transform. But if we know one, then we can automatically know the other, for example, like this. Okay, so that's a 2D Fourier integral to get this. So now, let's have an example of Fourier transform practice. So by the way, why are we doing this? Why are you studying and learning about Fourier transform? Just to remind you, previously, we have far field approximation of a wave propagation that turns out to be, we call Frohnhoff diffraction. It turns out to be the input Fourier transform is onto far field. That's exactly why. So that's why we are practicing this. So let's see, if there is an opening like a slit, then you can mathematically describe slit like this. Okay, then this is so-called a rect function. The area under the curve is 1, so this x is minus half to plus half. Its value is 1. Otherwise, it's 0, and just mathematically at this time it's half. So that's a rect function. Then how? Consider the question of when there's a slit, you shine a plane wave, and what's going to happen in the far field, let's say distance of L, what's going to see what you can see on the screen? That's a question. And that question now become a very easy way to solve because you just do a two-dimensional Fourier transform. In this case, even 1D Fourier transform. So let's say GU, the definition is this function times e to the minus I to pi ux dx. And only the value exists over here. So that, you know, that gx becomes 1. And so you are integrating exponent, and that's very easy that you can put this exponent constant down. And what you will find, so you put half to this and minus half to here. And this is very familiar form. What you can see is this is minus I2 sine pi u. So minus I2 is canceled out, and you can find something similar form you have seen. It's a sine pi u of pi u. And this is a famous form in mathematics that we define even, it has a name for it that we call sinc function. And the real shape looks like this. And you can see sine always have 0 at, and the argument becomes 0, pi, 2 pi, and integer of pi. So 1, 2, 3 of this u. This is sinc function. So what you find, the rect function, Fourier transform is sinc function. And this will be what you will see on your screen. Okay. Now I want to remind you a little bit of a review session for the Fourier transform, because this is gonna be used for all your homeworks from today. So I want to make sure you understand this. But based on the original Fourier transform formula, these are all like kind of a obviously can be derived by you. But I just describe it here. For example, in spatial domain shift theorem. So what if we shift our slit or any pattern in space? What can happen in the in frequency domain or far field? That can be described as this, right? We shift f by x0, y0, then what happens is it remains exactly the same, but you will have a constant phase edit here, such as e to the minus I 2 pi u, that x0 plus 3 times y0. What if you shift it in not space, but spatial frequency domain? And that you can describe it as fu minus u0, v minus v0. So if you shift that one and that one go back very similar, but you can see only the signs are different. Okay, let's consider another thing as a scaling theorem. What if in space domain it's becomes scaled by a factor of a and b, and in spatial frequency domain, you know, in space domain, if the length is x, in spatial frequency domain, it becomes 1 over length scale. So reminding that, in fact, it just changes as u divided by a, v divided by b. So this one as home exercise for you to practice yourself, these theorems yourself on the definition, based on the definition of Fourier transform. All right. So let's do a little bit of an example. Yeah. So what if in the spatial frequency domain, there's a shift by spatial frequency of u sub 0, then the sinc is not just u minus u sub 0. So then how can you calculate the original form? And that one, you go back to here, like this one, you just multiply by this. So you can multiply by e to the I 2 pi u sub 0 times x to the original rect function, because you know already sinc function was coming from rect function Fourier transform. And so from here, you want to find out what are the real and imaginary component, which is coming from here. So that's easily understandable. And let's move on to scaling theorem again. So this is something relevant to like energy conservation. If in space domain is elongated by a factor of a, you realize spatial frequency domain is actually elongated by the inverse of the factor. And to prove that, I brought this one. What if the rect function and physically the slit size is elongated by a factor of a, then instead of 1 over 2, a over 2. So you can define this way, and you will realize this rect function in spatial frequency domain, it's a sinc function, but instead of x over a, this is like expansion by the factor of a, because you have to get this the same value, you have to expand the x multiplied by a, and that becomes actually the inverse. So a sinc times a u. And what that means is, in this case, because this first and second was already originally 1, 2, 3, now you actually shrink by a factor of A. This one expand by a factor of A, and spatial frequency domain, it shrinks by a factor of A. So that's we call scaling theorem. So the theorems I put back as a shift theorem in space domain and spatial frequency domain. And this one is described as this, and scaling theorem more you can generalize of the scaling onto X and Y direction with different factor, then you can see it this way. And now, the most important aspect of why we learn about Fourier optics is the beauty of a mathematical description of this, and calculating and finding out and estimating what happens on your screen. So you remember that when we describe about Fresnel diffraction, so let's say original function of f as an input, and you want to propagate them through some space, and you want to find out electric field distribution. Remember that that happens to be a form of convolution. And that was how you can find these screens electric field distribution. In fact, this convolution is mathematically very neat in terms of when you look at this in the frequency domain, then convolution becomes just simple multiplication of each Fourier transform. And just likewise, if you have a multiplication in space domain, it actually comes from in spatial frequency domain that was convolution. And here comes the definition of convolution of F and H. The reason why we put H is H later will stand for point spread function, which we normally say about resolution. Okay, so that convolution is the we are convolving with respect to x, then the answer will have x prime. So you will have x prime minus x argument for one, and the other is x. And this can be exchangeable. You can find it out.